Okay, it's the Linuxfest, so we want to get this thing started here. All right, first I want to do a couple of acknowledgments. Thanks to the O.L.D 2023 for presenting us this year. We're very appreciative for the opportunity to be here and make this presentation before you. Thanks to Vance for all the technical support and all the extra effort and all of the back and forth and everything he did to help us pull this presentation off. I also want to give a shout out to George Mason University and the library research specialist there, Trevor Watkins, and helping us and sponsoring us with this Zoom connection. They're making this Zoom opportunity possible. And we want to give a thanks to our sponsor, C-Test Laboratories. That's where we do most of our daytime work, and they're very good at sponsoring us, and they provide a lot of support for our efforts, our side efforts to promote citizen science. We believe a lot in that, and so C-Test Laboratories has been very supportive in any kind of effort and endeavor that we've decided to pursue in that regard. So we're fortunate, and so we thank our sponsors here. And also we want to let you know, here's the URL on this slide for this video. It's going to be on YouTube, so you'll be able to access it from the YouTube page, and it'll be available for a link from Linuxfest 2023 as well. And so you will be able to access this. So for those of you that can hear the Zoom and you don't know where we are, you're not able to actually be here today, or you're off-site for whatever reason, you couldn't attend the conference, you'll be able to access this video. As well, we've provided a URL for supporting videos, videos related to the material that we're going to be presented today. We're going to do like a 45 or 50-minute talk, and this talk's got a lot in it, and so there will be a need to follow up on some of the material and check some of the references, and you may need to come back to it again. And so there are other videos that support some of the more involved concepts that we're going to talk about. So please take advantage of those and be aware of those here. At C-Test Laboratories, Tracy and I, our primary function is computational epistemology and epistemic visualization. And those are big words for we focus on methods of putting knowledge inside of computer programs, getting knowledge inside of a computer. Not just data and information, but how do we get knowledge? How do we represent the knowledge? Our main focus is on coming up with methods and algorithms, discrete structures and data structures, and different computational approaches to storing knowledge, retrieving knowledge, and finding knowledge in a computational context. And so that's kind of what Tracy and I do. And when we are not largely focused on that, we have a lot of volunteer efforts with citizen science in our neighborhood. We're in Youngstown, Ohio, and so on. We work very closely with the Oak Hill Collaborative Makerspace there, and we do volunteer work there, volunteer teaching engineering to any of the citizens and folks that live in the neighborhood, young and old. We support a lot of citizen science efforts. We are engaged in a lot of local lake and water testing, watershed testing, and that kind of thing. environmental monitoring. That's the kind of stuff that we do for the citizen science effort and support at CTEST Labs. And so this talk is kind of coming from that area. So that's enough. You can check us out on ctestlabs.org if you want to find out more about the kind of projects that we're both engaged in, or if you're trying to get in touch with us. I believe you can get our emails directly from that site. Okay, now as far as the matrix of, we try to score our videos in a way that will let the people in the audience know what to expect, and whether this the talk that you're getting ready to hear right now, whether it's too easy for you, it is too at a low level, and maybe you're already beyond this point, or whether it's maybe it's not something you're interested in, or maybe it's the material might be too advanced for you. So we try to get come up with a matrix and to give you some idea of the level of knowledge that the audience needs to participate in this. So on the Linux level, we're really talking about just beginning level Linux stuff, nothing really fancy there. The same thing with the Arduino. If you know basic wiring with the Arduino and you're kind of familiar with the Arduino environment, there won't be any surprises here. Raspberry Pi, the same thing there. And we put intermediate here because we talk about the GPIO pins a little. And so we realize there's some people who use the Raspberry Pi and they don't get into the pin programming at all. And so, that might be considered an intermediate. And then there's some folks that use the Raspberry Pi and that's all they do is the GPIO pins. And so for them, some of this may be beginning. C++, and that is primarily the language that we use at CTEST too, as well, and in all of our efforts. This is intermediate level stuff. We will at least talk about how implementing certain kinds of member functions. But if you know basic C++, you'll be able to follow and sing along, right? Prolog is beginning knowledge. For those of you who know what Prolog is, that's a programming language where logic programming techniques are used. You can, if you're familiar with GNU Prolog or Switch Prolog out of Amsterdam, you'll be very familiar with this. It's very beginning stuff. And the knowledge, representation, and reasoning aspect that we talk about is just beginners. And the same thing with descriptive logics. So this is a lot, and some of it could be dense, the stuff that's not beginning, and not everybody will necessarily get this the first time through. So fortunately, it's on video, and so you'll be able to, rewind, stop, pause, go back to it, and get yourself a drink and come back to it at a later time. So good that it's on video. And now, for who this is for, we kind of see this talk is for five people, there are five different categories of people, and you're going to have to select to see which one of those categories you're in. So category one, if you are a Linux, Arduino, or Pi programmer with just way too much time on your hand, then this talk is probably for you, okay? Also, category two, if you're a sci-fi hacker who has been secretly developing your own private thinking machine and you're missing just a few pieces of information, something you can't just quite get there, this talk could be for you. If you are an AI researcher out there and you're just a tad bit suspicious about all of this chat GPT stuff, this talk could definitely be for you. There's no question about that. If you're in category 4 and you've had no other session to go to this morning, and you got caught up by the clickbait title of this talk, right? For you, this should be a wild ride, and hold on, right? And the last category we have, if you believe you are the last Jedi, or the Kwisatz Haderach, or you're the chosen one, and you feel no one understands your strange Arduino Pi Linux creations, then this talk is definitely for you. And maybe you should drop us an email at CTES Labs at your earliest convenience. Now, if you don't feel like you're in any of these categories, right, and you manage to survive till the end of the talk, then drop us a note in the comments and let us know what you thought, and let us know what categories we should add in the future when we make this talk. And the title of this talk is Arduino meets Raspberry Pi, O.L.D. Programming Techniques for Knowledge Embedded Systems. And O.L.D. is an acronym, and we'll get into that. That's kind of like a double entendre, because some of the techniques we are talking about are really true and tried, and they've been around in the thinking machines community for some time. But some of it is state-of-the-art stuff too. So O.L.D. is kind of just a play on terms here. Here's another important point that we don't want to leave out. As far as the term artificial intelligence, this is a disclaimer here. The AI is being hyped. That term in the abbreviation AI has been hyped and applied to so many technologies in so many different ways, with so many vague expectations and so many just weird notions, with so many contradictory and undefined features, that we really don't even know what the phrase artificial intelligence even means anymore. AI, we can't put our finger in it anymore, so we just don't use it. And so we won't talk about it beyond this slide. Okay, so you may be, as you're listening to our talk, placing this in various AI categories, and you're welcome to do it. We're just letting you know that we won't be using the acronym, the abbreviation, or the term artificial intelligence for the rest of the slide. That's just kind of like this is just a disclaimer, just so we won't, fray any expectations here. Also, this is only old programming techniques. There will be no discussion of ChatGPT. So for those of you that are looking for that kind of thing, it's not going to be here. Won't be any talk about machine learning or deep learning or large language models. All of those of you out there that are looking for the latest and greatest and web programming, we're sorry. There's none of that going on. No Rust, no Node.js, none of those things. This talk is really going to be just focused on embedded type programming, microcontroller, Raspberry Pi level stuff, and that's the gist of it, right? And so if you're looking for that other kind of stuff, this probably is not your talk, right? And so we've got embedded devices, and what those are, and we've got this Arduino and Raspberry Pi combo, and we're developing these devices, and the point of these devices is to do environmental monitoring, and we're really talking about home level, do-it-yourself environmental monitoring, and of course, a lot of these devices, at least not the thinking versions, you can get simpler versions, off of Amazon for $40 or $50. So, it's not like this is some kind of breakthrough technology. This is for those, those hackers and those tinkerers and those programmers that want to make their own, and they've got the time to do that, and they want to make something that is knowledge based and that will give them a little more bang for the buck, and it's just interesting programming for them. And so the kind of monitoring we're doing and making autonomous devices for, I might monitor things like carbon monoxide or other dangerous exhausts that could be in your home. Maybe you got a soldering bench and and you don't realize, how much of that solder has gotten into the air, and so your system is going to let you know that. Fire, smoke alarms, all kind of things for indoor environment. Also, outdoor monitoring. Any kind of like monitoring your lawn, your garden, those kind of things. The soil monitoring, checking salinity and connectivity, pH, nitrate levels, all that kind of stuff. And if you need an autonomous embedded device that helps you monitor, maybe you got a small farm or small garden or something that you're trying to monitor, keep the flowers growing, something like that. We give you ideas and an approach to do this and build a system on your own that has some heft to it. Also, we're into the local lake watershed testing for harmful algae bloom. Like if you were to go to our site, you would see some of the underwater robots that we use. We have sensors and cameras attached to those things, and we have smart devices that we've designed to be a part of those that help us do watering, monitoring of like park lakes and recreational lakes in the Northeast Ohio. Like for instance, we have a Mill Creek Park Lake project where we're working on doing a video survey, underwater video survey of some of the Mill Creek Park lakes, like Lake Newport, Lake Dozier, Lake Glacier, some of those different lakes. So these are all environmental monitoring devices that you can build using a combination of Arduino and Raspberry Pi, and some of the techniques, the old programming techniques that we're going to talk about today, and give you an overview today. If you apply those, you'll come up with something that'll give you monitoring ability, autonomous monitoring ability, but this has way more functionality than something you might buy on Amazon, right? And so for those of you that are the do-it-yourself types, or folks with some of those Arduino and Raspberry Pi programmers that have way too much time on their hand, here are a couple good book references. They have some real easy and interesting projects in them. They're pretty inexpensive from what I remember. They're like under $10, these things. And so if you were looking for ideas for environmental monitoring and little projects with examples and that kind of thing, these are good starter type things, stuff that will kind of inspire your imagination with respect to atmospheric monitoring or environmental monitoring. And I recommend them. I have them. I've used them. I use them in classes. They're good books for what they are, and for the cost, you really can't beat them. You're done by O'Reilly and MakerPress. So this is good stuff. And so for those of you that are interested in this kind of thing, this is a good place to start, right? And so we have the Arduino and Raspberry Pi and the Raspberry Pi OS. It's like a trio here that a lot of times people just refer to the Pi and they're just thinking about the hardware. But boy, that Linux basis, the Raspberry Pi OS is with all of the tools and utilities and the access and availability and the applications that are available in a Linux environment. It's a powerhouse in its own right. And so we use these three things together. First of all, there are things that we need to do as far as sensors and dedicated effectors and actuators that the Arduino is best for, right? That's what it has. The ports, it has the pins. It's designed real well for that. It has the price point for that. It's a nice little microcontroller, and so we have dedicated things that we do on the Arduino. And then the Raspberry Pi just has way more capability at a higher level, having that ability to attach external storage and HDMI monitors or whatever it is that we might want to attach to it. The Arduino brings that, the Raspberry Pi brings that bigger thing, and then we have the entire Linux environment with the free and open source software that just allows us to do things from a citizen science level, and it just brings down the cost and makes it accessible to people that need to do this kind of stuff, or that want to do this kind of stuff. So the Arduino and Raspberry Pi and the Raspberry OS for us, it's a nice trio for a lot of reasons. Some of them, beyond those I just mentioned, are just the sensors that are available. If you're doing monitoring type and measurement type work, the Arduino and the Raspberry Pi, they are your friends. You can find a whole bunch of sensors in a wide range of application areas that are just readily available for both the Raspberry Pi and the Arduino. The ultrasonic sensors, connectivity sensors, magnetic sensors, tilt, gyroscopes, communications, soil, oxygen, just about anything that you want to get at in terms of home, do-it-yourself environmental monitoring. There's a Raspberry Pi or Arduino sensor out there for you, and if not, a combination of those sensors can give you a little bit even more functionality. So as a wide sensor array, these things are also very affordable. You get packs of them for, in some cases, under $100. So that was another reason why we went to Arduino and Raspberry Pi to build our embedded devices, because the availability of sensors is just rich. And folks that know a lot about sensors are part of the Arduino and Raspberry Pi community. And so for those of us that need help with that kind of thing, there's plenty of folks out there that will help you and that are knowledgeable about that. And also the folks at the NIST, there's some folks behind the scenes there that work with the Arduino and Raspberry Pi community. National Institutes of Science, Standards and Technology. Those folks, they have some good people there. And as a matter of fact, in any of the 17 national labs, at least the ones we work with, there are people that will work with you behind the scenes on some of those, and they work with your school and that kind of thing. So anyway, sensors was a big thing. For the Arduino, that Arduino programming environment was also a big reason why we picked that. It makes programming these microcontrollers, it makes it very accessible, a lot more accessible and a lot more open than some other environments. I won't mention names. And the support that Arduino has for C++ and object-oriented programming. And make no mistake about this, the programming environment for Arduino is a subset of C++. There are obviously, because it's a microcontroller, there are obviously things that you can't bring the full set of class libraries in, and the full set of memory management and those kinds of things in. But it's a legitimate subset of C++. It's not some strange variant of C. I hear that a lot of times. People think that the Arduino is some kind of a C because when they boot up the environment, all they see is a setup and a loop function, and they don't really see the C++ they're used to. But those functions are really just convenient candy functions, sugar functions out there to make things easier. There's a main line, and there's you can get at regular C++ in the Arduino environment. So it has full support, or at least as much of the support for object-oriented programming that we need. And in the object-oriented programming that we use, we implement a lot of procedural and declarative knowledge techniques using that. So the Arduino environment is perfect for us in terms of the microcontroller programming, and so that was a big thing. And then the Raspberry Pi, you just can't beat this thing with all of the capabilities, the Ethernet capability, USB access, the storage, the processor speed, you know, the HDMI. It's just, and it has the GPIO, these 40 GPIO pins that lets you program, serial programming, I2C kind of programming if you've got the courage for that. It's just a wealth for people that are trying to do low-level programming that you can't beat it. It's 5-volt power, 3-volt power, UART kind of programming. You got the clocks that you have. It's just, for people who are doing microcontroller, microcomputer, pocket mobile microcomputer, or computing kind of applications, the Raspberry Pi is like, and it's Linux based, it's just a powerhouse. And so that's also the camera, like we, in a lot of our applications, we have a camera component. We're running OpenCV on there for object recognition. It's just, a powerhouse, right? So you couple this with the Arduino and Raspberry Pi OS, and you really have something to work with. Okay, so let's get right quick here. We're going to talk about this O.L.D architecture, and we're just giving like a simple overview right here. It's we're just kind of giving a logical view of a knowledge-based embedded device, and keep in mind that these embedded devices are used in physical computing most of the time, and I guess I want to distinguish physical computing from like desktop computing or web computing, you know what I mean, where in the physical computing you're using the device in as a part of some other process, outside of a, say a business application or something. But that's a whole nother talk. A whole nother discussion in of itself. Let's just suffice it to say that we're talking about knowledge-based devices that are used primarily in physical computing. And in this case, the physical computing application is environmental monitoring. Now, in our O.L.D architecture, so we're going to talk a little bit more in a minute here about what O.L.D means. But in this O.L.D architecture, it's an agent-based architecture. So we have two agents. We have one agent that runs on the Raspberry Pi, and we have one agent that runs on the Arduino. The Arduino agent it has procedural knowledge about sensors, effectors, and actuators. The Arduino agent has C++ models, detailed models of specific sensors, specific actuators, specific effectors. So it's the device-specific knowledge that we model and that we run on the Arduino. Okay, so if I am using a particular, let's say a HRSO4 ultrasonic sensor, then the model of that sensor, that specific sensor, has been implemented and is running in the Arduino environment. Okay, and on the Raspberry Pi, we also have a sensor agent there, and on that sensor agent, it has access to the knowledge base that we're kind of alluding to. It has access to algorithms that we call reasoners and inference. It also has high-level sensor models. And so what we mean by high-level sensor models, it may know how to interact with let's say an ultrasonic sensor or a light sensor or a magnetic sensor at the high level, but it doesn't have any knowledge about a particular ultrasonic sensor or a particular conductivity sensor, right? And so that kind of knowledge is actually stored in the class that's running on the Arduino. So if you look at it, the Raspberry Pi agent has high-level knowledge about sensors, effectors, and actuators, and it has models of those things. And the Arduino has low-level, detailed, device-specific models of manufacture vendor-specific models of those kind of things. And then we have the Raspberry Pi. So it's kind of a dual agent thing. One agent runs on the Raspberry Pi, one agent runs on the Arduino. The Raspberry Pi is more generic with respect to the hardware. Our Arduino is more specific with respect to the hardware. So kind of keep this picture in mind as we're going. And the devices that we are running need both of these components, right? Where you know, for the architecture that we're talking about, you can't just have a Raspberry Pi. I mean, you could just have a Raspberry Pi, but it's going to make a lot of your programming harder, and you're going to be taxing those GPIO pins beyond what you need to. And so it just makes better sense to distribute that work. Okay. And so what do we mean by O.L.D? It's an acronym. O.L.D, the O is for object-oriented programming, the L is for logic programming, and the D is for descriptive logics. And we use those three concepts to help us develop embedded, knowledge-based, agent-oriented systems that can think about the monitoring process. Okay, and when we highlight think here, we really do mean that. And we say O.L.D again as it's an acronym, but yeah, these concepts have been around. These are true tried things, and they aren't going anywhere. And for the work that we do, these are the best techniques and approaches to architecture that we've been able to come up with. And we've been at this for a few years now. And so we stick with these things. And it's an approach to using Arduino and a Raspberry Pi. We feel that will help you, if you're trying to do this kind of work, it will help you be more, you'll get a better handle on your projects. You'll be able to maintain them better, understand them better. You'll be able to apply them in more areas. And so C++ is the primary thing that we have going on. And then on the logic programming side, on the Raspberry Pi, we use switch prolog. That's what we call it. We've got a link here on the slide. Some of you may have never even heard of this before. I don't even know what Wikipedia says about this language. I just know that in the logic community, it's a big deal, and as far as we're concerned, it's state of the art in many ways. Others may see this as a language from days gone by, but I assure you it's alive and well. There's a GNU prolog, but we didn't find it flexible enough to do what we were trying to do, and so we went with switch prolog, which is also an open source technology. So anyway, the old programming techniques that we're talking about involve object-oriented programming, logic programming concepts, and descriptive logic programming concepts. And combining those things together, we're able to make these systems that can think about the monitoring process. And so what do we mean by think, right? That's a charged word. And so at CTES Labs, we kind of define it by a list of terms, right? So for us, it's these operations here: evaluating, calculating, computing, analyzing, supposing, positing, deducing. It's those kinds of things. Notice we have some of these terms in red. These terms, although a part of thinking, we do not implement those. And so we haven't been able to do pondering and innovating and wondering and imagining yet. We'll save that for other kinds of ambitious software, but the other ones we do, and there we have very specific algorithms and procedures and programs and functions that implement these kinds of operations, and they are running on the Raspberry Pi and on the Arduino, right? So these are not things that require massive supercomputers running in the cloud and all this kind of stuff. We don't have that going on. We're talking about everything we're talking about today actually executes right on the Arduino and the Raspberry Pi, and so these thinking operations are done. And we're going to give you references to this kind of programming at the end of this talk. But this is all done with epistemic and dosastic and deontic temporal logic frameworks. Again, I wouldn't be bringing them up if we couldn't implement this stuff in a Raspberry Pi and Arduino environment, but we can. And so when we say thinking, this is what we mean, and these are the kind of operations we're talking about. And now we keep saying knowledge base. I want to differentiate and just contrast a knowledge base to a database. So when we say knowledge base and knowledge based, you can kind of picture what we're talking about. In a database is typically going to just store, a collection of data and information. That's what it does. And the kind of operations you get happening on a database, you get selection, and I'm just using SQL, SQL here. You get selection operations, union, intersection, subtract, those kind of operations. You do that on the data and information that's stored in a database, and that's what happens. A knowledge base is a very different thing. Contrary to some of the things you might see on the web where they show knowledge base just being a collection of frequently asked questions, that's not what it is in our community, in the KIR community. Knowledge base is a very technical thing, and it's a set of propositions, and it has a set of reasoner type operations. The operations that you do, where you do selection, union, and intersection on a database, on a knowledge base, you're going to do assertion, deduction, abduction, induction, retraction, logical type operations. So a knowledge base has a collection of propositions, and database has just data and information. Very different things, very different kind of processing. And just for those of you who are trying to look ahead, the knowledge base runs on the Raspberry Pi. And we also want to make this point, there's different kind of proposition types using knowledge bases. We got like 9 of them here. You got rules and facts, and you got axioms, theorems, conjectures, suppositions, corollaries, lemmas, and assertions. Those are all different kinds of proposition types that are stored inside of a knowledge base. So whatever is in the knowledge base is going to be one of these kind of things, one or more of these kind of things you see in this table here. We use these type of propositions to give our devices, our smart devices, the ability to think, right? To perform those operations that we talked about in the previous slide, right? And so keep that in mind. These operations here, we use those propositions to perform these kind of operations, just so everyone has that in mind here. And again, in our embedded systems, the knowledge base is stored on the Raspberry Pi, right? Okay, and what do we mean by agents? So we talked about there's an agent that runs on the Arduino, and we talk about there's an agent that runs on the Raspberry Pi. Well, for our purposes and the development that we do, an agent is an autonomous, knowledge-based program, right? It is not something that is interactive. You're not going to be pointing and clicking with a mouse to use it. This is something that is these are autonomous programs. The program that runs on the Arduino, those of you that are familiar, the minute the Arduino gets power, it just starts running whatever has been stored on it. And on the Raspberry Pi end of things, we launched that Arduino as a part of System D with a System D timer or with a cron tab scenario. So it runs at all times as well. And it runs immediate. And it's autonomous. So whatever it's going to do, it does that without your input or with very little input from you, just enough to get it started. Okay, and so the agent types, there are a lot of those out there. Those of you that are hearing the term agent for the first time, you might quickly run to do a fact check on us and jump on the web and see what you can see. And you're going to find out there are lots of different types of agents. The ones that are relevant to what we're talking about today: rational, epistemic, hysteretic, utility, tropistic, and deliberate. Those are relevant to the kind of agents that we're talking about today. But specifically, the agents that we develop at CTES Labs are epistemic agents. Now, epistemic agents are basically knowledge-based agents. Agents where knowledge is the primary focus of the function of what that agent is. So we have epistemic highlighted here. And so if you really want to dig down deep and try to see what's going on at maybe the formal level or the conceptual level, you might look up epistemic agents on Wikipedia or something. It might excite you in some kind of way. Okay, and now we're going to give just a brief overview of the programming techniques. Try to give you a little more detail on it. Okay, so there are two C++ classes. One of those classes is going to be defining the Arduino sensor agent. The other is going to be defining the Raspberry Pi sensor agent. So keep that in mind. To do this programming technique concept, you have two different classes. One class runs on the Arduino. The other class runs on the Raspberry Pi. The Arduino sensor agent is going to be a specialist. It's a sensor specialist, it's an effector specialist, and it's an actuator specialist. In essence, that means it's going to have the models of the device-specific things that you have attached to your Arduino. If you've got a magnetic sensor attached to your Arduino, then your Arduino agent is going to be a magnetic sensor agent, and it's going to have a model, a C++ class model of that magnetic sensor. That's what this is referring to here. And on the Raspberry Pi is going to be an environmental specialist, right? And a measurement specialist. And I say that, like, for instance, in one of our applications that we just did recently, we did for Robot Week, we were measuring the salinity of soil, how much salt is in the soil. And so that Pi agent needed to have a lot of knowledge about soil salinity and measuring soil salinity. So it's a specialist in that regard. It also knows something about the sensors. It's a generalist in that specific sense. And it's a generalist at the effector level, and it's a generalist at the actuator level. Like, for instance, to measure salinity in the soil, any soil, and this could be soil, your front yard or backyard, you could use something called a conductivity sensor, electroconductivity sensor. How conductive is the soil in your front yard or backyard, and the Raspberry Pi sensor agent generally knows what a conductivity sensor is. It has a general knowledge of that. And Arduino sensor, in our case, we use something called a veneer conductivity sensor. The Arduino sensor had very specific knowledge of that veneer sensor. It knew what modes that sensor operated in. It knew what the voltage translation was for that particular sensor. It knew what the slope and the intercept was for that sensor. It had very detailed knowledge of that particular vendor sensor. Whereas the Raspberry Pi sensor agent, it knew the function of a conductivity sensor and what kind of readings you should get back from it and what those readings should mean. On the other hand, the Arduino sensor, it doesn't know what those readings mean. It knows how to get them, it knows how to be specific, but it doesn't have any environmental or real measurement knowledge. The Raspberry Pi has that. You'll be able to see that as you get into this kind of a design. One of the agents has a high level knowledge of things, and the other agent has the very low level knowledge of things. Also, you have a Arduino sensor agent.h file where you declare the class, and a .cc file, .cpp file for those of you that prefer the CPP thing. You define those two files, and here's an important point. You put those in that Arduino/libraries directory. I have library singular here, but that's libraries plural. Libraries directory. You do not put the class declaration and the class implementation in the setup and loop functions. That's just going to get you into trouble. Okay, so those of you that are beginning, just your beginners at the Arduino programming thing, I'm letting you know now. You find the directory on your computer that has Arduino at the head of it, and you go to the libraries subdirectory, and then you create a directory for your Arduino sensor agent.h and .cc files. And you will also have Pi sensor agent.h and PySensor agent.cc. You put those wherever you want. That's a Linux development environment on the Raspberry Pi OS, and so you'll know where all of that stuff is and where to put it. It just, you want to put this, when you get to the Arduino, it needs to go in a certain specific place. Okay. Also, just dividing between the functionality between the Pi sensor agent and the Arduino sensor agent. The Arduino sensor agent, the member functions. Okay, so keep in mind a C++ class is a set of attributes and member functions. The member functions implement device-specific procedural knowledge. Okay, I do not have time here to define what procedural knowledge is. But it's the knowledge of how to. I can give you just a brief kind of, a quick kind of thing, like the knowledge of how to ride a bike, or how to jump a car, or that kind of knowledge. The member function on the Arduino class, they implement procedural knowledge. That's one of the reasons why we call it knowledge based, because it has particular kinds of knowledge that it implements.